The story of Rutherford's transformation of early scientific instruments is not simply a tale of improvement. It is a turning point in the evolution of experimental physics itself. Before Rutherford stepped into the arena, radioactivity was a mysterious phenomenon, intriguing, unpredictable, and nearly impossible to measure with accuracy. The tools available to scientists of the late 19th century were not designed to detect the faint, invisible signals produced by radioactive materials. What existed were rough, unreliable devices that could only provide broad guesses, not precise measurements. Yet, when Rutherford began his work, he brought to the lab something more important than tools. He brought a mindset. To him, the limitations of instruments were not barriers, but invitations to innovate. He believed that if nature produced signals, humans could find a way to detect them clearly, consistently, and scientifically. It was in this spirit that Rutherford revolutionized the very instruments that enabled the birth of radioactivity science. At the time Rutherford began his research, scientists had only recently discovered that certain elements emitted strange rays, which could fog photographic plates, affect electric charges, or penetrate materials, but none of the existing instruments were sensitive enough to capture the nuances of these rays. The early devices could barely detect radioactivity at all, and when they did, the measurements fluctuated wildly, leaving researchers confused. This was a period where science had curiosity, but lacked the equipment to explore it. Rutherford recognized immediately that understanding radioactivity required instruments capable of detecting signals that were millions of times weaker than ordinary physical effects. To him, the precision of measurement was not optional. It was the foundation upon which the entire field of nuclear science needed to be built. One of Rutherford's earliest and most important contributions was his refinement of the electrometer, an instrument originally designed to detect electric charge. Prior to Rutherford, electrometers were clumsy and unstable. They drifted, they reacted to temperature changes, and they lacked the sensitivity required to detect the tiny currents produced by radioactive decay. Rutherford took this device and pushed it into a completely new realm of performance. He modified its components, stabilized its materials, and refined its calibration method until it was capable of detecting charges so small that many scientists did not even believe such precision was possible. The electrometer became, in Rutherford's hands, a tool of extraordinary sensitivity. It could measure the faint ionization produced when radiation passed through air, something no one else had achieved reliably before. But Rutherford's genius went far beyond improving instruments. He changed the purpose of instruments. He believed that tools were not passive objects. They were active participants in discovery. To Rutherford, each device was a collaborator that had to be understood, trained, and optimized to reveal the hidden truths of nature. That is why he spent long days and nights testing his instruments, adjusting screws, replacing wires, recalibrating meters, and repeating experiments again and again with monastic dedication. He approached tools with a blend of engineering, patience, and imagination. If a device could not capture a phenomenon clearly, he did not give up on the phenomenon. He rebuilt the device. Rutherford also introduced new ways of measuring radioactivity that had never been used before. For example, he developed methods to observe the rate at which radioactive substances emitted particles by counting ionization events. This was revolutionary because it transformed radioactivity from a vague glow into a measurable quantity. Instead of saying, "This material seems more active than that one," scientists could now say, "This material releases this many particles per second." This ability to quantify changed everything. Radioactivity became a mathematical science, governed by principles that could be tested, reproduced, and refined. Another major transformation came from Rutherford's work with alpha and beta particles. Before him, researchers did not even fully understand what these particles were, let alone have tools to measure them properly. Rutherford realized that to understand these mysterious emissions, he needed tools capable of separating, tracking, and identifying different types of radiation. Working with magnetic fields, charged plates, chambers of air, and various thin materials, he built experimental setups that could detect how different particles behaved under controlled conditions. These configurations, many of them improvised from seemingly ordinary materials, became the forerunners of instruments still used in nuclear physics labs today. Rutherford's tools also allowed him to measure the speed of particles, their range in air, their ability to ionize gas, and their behavior when exposed to electric or magnetic fields. Each measurement revealed something crucial about the structure of the atom. Without his refined instruments, these discoveries would have remained buried under layers of scientific uncertainty. His innovations did more than create better instruments, they created better scientists. Other researchers around the world began to adopt Rutherford's methods and use his devices. Suddenly, laboratories that had struggled to obtain accurate results were able to measure radioactivity with unprecedented clarity. His tools democratized nuclear research, allowing a new generation of physicists to explore a field that had previously been limited by technical constraints. Another important transformation brought by Rutherford was the principle of reproducibility. Before he came along, many experiments related to radioactivity produced inconsistent results. Two scientists could test the same material and achieve entirely different measurements. Rutherford changed this by designing instruments that were stable, predictable, and precise. Through multiple tests, he proved that radioactivity followed specific patterns. Its intensity decreased over time, its particles traveled in predictable paths, and its effects on matter could be quantified. This consistency allowed radioactivity to become a real scientific discipline instead of a scattered collection of interesting anomalies. Moreover, Rutherford's approach to instrumentation had a deeper philosophical impact. He established the idea that to understand nature's most subtle processes, scientists needed instruments that matched the sensitivity of the phenomena they studied. This approach influenced not only nuclear physics, but also fields such as chemistry, astronomy, and medicine. His emphasis on precision and innovation became a cornerstone of modern science. Rutherford also pioneered techniques for shielding instruments from environmental interference. He recognized that tiny drafts of air, vibrations from footsteps, or fluctuations in electrical supply could ruin experiments. He redesigned laboratory environments to minimize these disturbances, creating some of the first controlled environments dedicated to atomic research. This level of attention to detail set new standards for laboratory work worldwide. Even more importantly, Rutherford's transformations were not limited to physical tools. He also refined the methods of measurement. He introduced systematic calibration procedures, comparative testing, and error analysis. These practices would later become essential components of scientific experimentation. Every student trained in physics or chemistry today, knowingly or unknowingly, follows principles introduced by Rutherford. Though many of his instruments appear simple by modern standards, their impact cannot be overstated. They represented a fundamental shift from observational science to precision science. With each refinement, Rutherford unlocked new levels of understanding about the invisible world of subatomic particles. Without these tools, the gold foil experiment, which revealed the nucleus, could never have been conducted. Without these instruments, the concept of the half-life would have remained unknown. Without his improvements, the field of nuclear physics might have been delayed by decades. His tools ultimately gave birth to technologies we now take for granted: radiation detectors in hospitals, nuclear energy measurement devices, radioisotope tracking, and countless diagnostic machines. All of these technologies can trace their ancestry to Rutherford's reimagined instruments. Rutherford transformed crude tools into precision instruments not by accident, not by luck, and not by following established paths. He transformed them because he believed that the smallest signals of nature deserved the sharpest attention. His instruments did not merely measure radioactivity, they elevated it from mystery to science. They took humanity from the dim understanding of invisible rays to the luminous clarity of atomic structure. And they proved, long before modern technology existed, that the human mind could build bridges to the unseen world. His tools were not just devices, they were extensions of his scientific vision. They were the lenses through which humanity glimpsed the birth of radioactivity, science itself. One of Rutherford's greatest strengths was his capacity to see the hidden potential in devices considered too crude for serious scientific inquiry. He didn't dismiss an instrument simply because it was imperfect. Instead, he saw imperfection as an opportunity for engineering creativity. His electrometer, for example, went through countless modifications. Every time he noticed an inconsistency in its measurements, he did not blame the experiment. He re-engineered the device. He replaced unstable materials with more temperature-resistant components. He redesigned its supports to reduce vibration. He improved the insulation of its wires to eliminate unwanted charges. Through dozens of small improvements, the electrometer became more sensitive, more reliable, and more capable of detecting the tiny electric currents created when radiation ionized air molecules. Many of these upgrades were inspired not by the needs of physics alone, but by Rutherford's engineering instincts. He treated scientific instruments like works in progress, always capable of one more improvement. As Rutherford refined his tools, he began to discover patterns in radioactive behavior that had eluded other scientists. Only with precise instruments could he notice how quickly ionization currents rose and fell, or how consistently alpha particles behaved under different conditions. These patterns were subtle, too faint for earlier researchers to notice, but they were essential for understanding how radioactive materials released energy. Rutherford's measurements revealed that radioactivity was not a chaotic phenomenon. It followed mathematical laws, displaying decay rates and particle emission patterns that could be calculated and predicted. Without the precision of his refined instruments, these patterns would have remained invisible. Because of his work, the science of radioactivity acquired its first theoretical foundations, rooted in repeatable measurements rather than speculation. One of the most remarkable outcomes of Rutherford's instrument transformation was the birth of the counting approach to radioactivity. Before him, scientists could observe effects, fogged plates, glowing screens, or shifts in electric charge, but they could not count how many particles were being emitted. Rutherford realized that ionization could act as a kind of clicker, each tiny electric charge marking the passage of a particle. This revolutionary concept turned radioactivity into something quantifiable. His refined electrometer could detect thousands of ionization events per second, giving him the ability to measure the activity of a sample with extraordinary precision. This move from qualitative to quantitative science changed everything. Now researchers could compare materials, calculate decay rates, and predict how radioactive substances would behave over time. The entire concept of half-life was built on the precision his instruments delivered. Rutherford's work also opened the door to the discovery of new radioactive elements. When measuring samples, he noticed that certain substances produced ionization patterns that didn't match known materials. His precision tools revealed variations in activity so subtle that they would have been invisible to anyone else. These subtle variations eventually contributed to the identification of radon and several other isotopes. Without accurate instruments, these new elements might never have been detected. Rutherford demonstrated that sometimes the existence of a new element is not revealed through bold visual clues, but through the faintest discrepancy in measurement. Another crucial aspect of Rutherford's instrument-based revolution was the development of methods to separate different types of radiation. Early researchers lumped together all forms of radiation, believing they were variations of the same mysterious emission. Rutherford's tools proved otherwise. Using electric and magnetic fields in combination with his detectors, he observed that some particles were deflected while others passed straight through. This simple observation became possible only because his instruments were sensitive enough to track the behavior of emissions under controlled forces. As a result, he classified radiation into alpha, beta, and eventually gamma types, each with distinctive properties. This classification laid the groundwork for modern nuclear physics and radiation medicine. Once again, the key was not merely observation, but precise measurement enabled by refined tools. Rutherford's improved instruments also changed how scientists perceived the structure of matter itself. Before his experiments, the atom was considered a solid ball or cloud of electric charges, a model that could not be tested due to lack of experimental precision. His upgraded detectors, however, captured the way alpha particles scattered after striking thin metal foils. The data produced by his instruments revealed patterns no one expected. Most particles passed through, but some bounced back, an astonishing discovery that contradicted all existing atomic theories. These results could not have been trusted without reliable instruments. The gold foil experiment, widely considered one of the most significant experiments in the history of science, relied entirely on the sensitivity and precision of Rutherford's measurement tools. Thus, the concept of a central atomic nucleus was born not only from clever thinking, but from the capabilities of instruments he had transformed. His contributions also extended to the development of ionization chambers, devices that became essential tools for measuring radiation for decades. Rutherford redesigned early versions to be more insulated, more stable, and more sensitive. He used these chambers to determine the penetration power of alpha and beta particles, gathering accurate data on how far each could travel in air. This work had profound consequences. It allowed researchers to predict how radiation would interact with different materials, and provided essential knowledge for fields such as nuclear safety, medical imaging, and radiation therapy. These improvements were not accidental. They were deliberate applications of Rutherford's belief that every physical phenomenon could be measured if instruments were advanced enough. Rutherford's transformed instruments also influenced how laboratories were built. Before his time, labs were not designed with atomics, scale measurements in mind. Environmental disturbances such as drafts, vibrations, and temperature fluctuations often interfered with experiments. Rutherford recognized that even the faintest disturbance could skew results. He introduced new laboratory practices, controlled airflow, isolated workbenches, vibration, resistant surfaces, and strict calibration routines. These changes improved not only his own results, but also set new standards for laboratories worldwide. As other scientists adopted his designs, precision in measurement became a global expectation rather than a rare achievement. His influence extended far beyond the walls of his lab. As other researchers observed the accuracy of Rutherford's results, they began to adopt and replicate his instruments across Europe and North America. His tools became templates, and his methods became protocols. Scientists no longer had to invent their own crude devices. They could now rely on Rutherford's refined designs. This spread of standardized instruments accelerated the growth of radioactivity research globally. Laboratories that once struggled to make sense of radiation now produced consistent, comparable results. This global collaboration was a direct outcome of Rutherford's insistence on precision. One of the most important long-term consequences of Rutherford's transformation of instruments was its impact on scientific culture. Before him, it was common for researchers to rely on intuition, rough estimates, or subjective observations. Rutherford replaced this approach with scientific discipline centered on accurate measurement, careful calibration, and rigorous testing. His students, many of whom became influential scientists themselves, absorbed this mentality and carried it into their own research careers. Through them, Rutherford's emphasis on precision spread to new fields such as quantum mechanics, nuclear chemistry, and particle physics. It is also important to highlight Rutherford's ability to blend simplicity with innovation. He did not rely on expensive or exotic materials. Instead, he repurposed everyday items into powerful instruments. Thin sheets of gold leaf, photographic plates, bits of metal, and magnetized coils became the ingredients of groundbreaking experiments. This practical ingenuity meant that scientists anywhere in the world, not just those with high funding, could replicate his methods. Even today, some of his designs remain iconic examples of scientific creativity under resource constraints. Another aspect of Rutherford's legacy was the shift in scientific attitude from passive observation to active exploration. Where other scientists saw limitations, Rutherford saw frontiers. When an instrument failed to capture data reliably, he didn't interpret that failure as the end of the investigation. Instead, he took it as evidence that a better instrument needed to be built. This mindset transformed not only tools, but the very philosophy of experimental physics. It encouraged scientists to believe that with enough creativity and precision, no natural phenomenon was beyond human understanding. Rutherford's refined tools also played a vital role in shaping the early structure of nuclear physics theories. As physicists attempted to model the atom, they relied heavily on data produced by Rutherford's experiments. The accuracy of his measurements gave theorists the confidence to build mathematical models that described the atom's internal structure. Without reliable data, these models would have been little more than speculative guesses. Because Rutherford provided the tools that supplied precise experimental evidence, he became one of the foundational pillars of modern theoretical physics. Another profound impact of Rutherford's transformed instruments was the advancement of radiation safety. As he and his colleagues became more familiar with the behavior of radioactive particles, they developed early guidelines for safe handling. His precise measurements revealed the different penetration abilities of alpha, beta, and gamma radiation, allowing scientists to predict potential hazards. Although full radiation safety standards would not be developed until later, Rutherford's measurements laid the groundwork for protecting future generations of researchers and medical professionals who work with radiation. Even fields not directly related to nuclear physics benefited from Rutherford's instrument innovations. Medical imaging techniques such as X-ray detectors, CT scan technologies, and radiation-based diagnostics all trace part of their lineage to the principles he established. Using ionization, counting events, measuring penetration, and analyzing particle behavior. These medical breakthroughs have saved countless lives, and their roots can be found in Rutherford's insistence that instruments can always be made more precise. In addition to scientific applications, Rutherford's instruments influenced industries such as geology, where radioactive dating techniques became vital tools for determining the age of rocks and fossils. His concepts of decay rates and measurement accuracy allowed researchers to calculate the half-lives of various isotopes. These methods revolutionized our understanding of Earth's history, transforming geology from a largely descriptive science into a quantitative one. Rutherford's approach to instrumentation also set the stage for modern particle detectors used in today's massive accelerators and research facilities. Although his tools were simple compared to modern silicon detectors and photomultiplier tubes, the philosophy behind them remains identical. Understand the limitations of the device, refine it until it can detect the smallest possible signal, and use it to explore the fundamental structure of matter. His work was the first step in a long journey that eventually led to the development of cloud chambers, Geiger counters, scintillation detectors, and sophisticated digital instruments used in high-energy physics. It becomes clear that Rutherford's transformation of crude instruments into precision tools was not a narrow technical achievement. It was a revolution that reshaped science itself. His instruments allowed him to uncover patterns in nature that had been invisible since the beginning of time. They enabled him to build the foundations of nuclear physics, to challenge existing theories, to inspire generations of researchers, and to unlock discoveries that continue to influence technology and society today. His tools were more than mechanical devices. They were catalysts for scientific evolution. The rise of Ernest Rutherford as the father of nuclear science didn't begin with the dramatic gold foil experiment or the revelation of the atomic nucleus. It began with something far less glamorous, an instrument that most physicists of his era considered too delicate, too unreliable, and too temperamental to be of much scientific use. The electrometer, before Rutherford got his hands on it, was a device that swung between promise and frustration. It was intended to measure electric charges, yet it was so easily disturbed by temperature, vibration, or even the static electricity in the room that no one really trusted it for serious research. But Rutherford saw something different. He saw potential. He saw a tool waiting to be transformed. And through relentless patience, engineering intuition, and scientific discipline, he turned the electrometer into one of the most precise instruments of early atomic physics. Part of this explanation dives into how Rutherford refined this fragile device until it became the key that unlocked the invisible world of radioactivity. To understand the significance of Rutherford's electrometer, one must first understand how primitive the scientific landscape was before his interventions. Radioactivity had been discovered, but it was still a mystery, an effect scientists could observe but not measure with any real precision. These emissions from uranium and thorium fogged photographic plates, produced weak electric currents, and caused chemicals to glow. But how strong were these emissions? How fast did they travel? How did they vary between materials? No one could say with confidence, because no one had the tools to peel back the quantitative truth of radioactivity. Many scientists tried to use early electrometers, but these devices drifted uncontrollably, reacting to environmental changes rather than the phenomenon they were supposed to measure. A breeze, a footstep, or even a slight fluctuation in room temperature could ruin an experiment. Most researchers abandoned the electrometer as a promising but flawed idea. Rutherford, on the other hand, had a different instinct. He believed that if nature produced a signal, even a faint one, the human mind was capable of building an instrument sensitive enough to detect it. When he began studying ionization, the process by which radiation strips electrons from air molecules, he knew the electrometer was the tool that could measure the resulting charges. But only if it was refined, stabilized, and re-engineered with greater precision than anyone had attempted. This belief was the beginning of one of Rutherford's most important contributions to scientific instrumentation. Rutherford approached the electrometer like both a physicist and an engineer. He didn't accept the device as it was. He treated it as a prototype with endless room for improvement. One of his first steps was to redesign its structural components. The original electrometers used soft metals and weak supports, which made the needle wobble or drift. Rutherford replaced these with more rigid materials, reducing wobble and ensuring that the needle responded only to actual electric charges. He also reconfigured the suspension system, altering the tension and balance of the needle so it moved smoothly and predictably. These structural changes alone improved the device's accuracy dramatically. But Rutherford didn't stop there. He realized that the electrometer's sensitivity was being compromised by environmental interference. A slight vibration in the lab floor could nudge the needle. A change in temperature could expand or contract its components, altering its measurements. Even the static charge from a person walking across the room could influence its readings. Rutherford addressed these issues in a methodical and innovative manner. He built insulated enclosures to shield the electrometer from temperature shifts. He mounted the instrument on vibration, resistant stands so footsteps or nearby activity didn't disturb it. He used grounded metal casings to protect it from stray static electricity. Each improvement brought the device closer to becoming a reliable scientific instrument. Another crucial refinement Rutherford introduced was improved calibration. Before him, electrometers were calibrated roughly, often using broad estimations rather than precise standards. Rutherford changed the entire calibration process. He developed methods to test the electrometer against known charges, adjusting the sensitivity of the device until its readings matched expected values with extraordinary consistency. This alone elevated the electrometer from experimental toy to precision instrument. He repeated calibration continuously, insisting that stability could only be achieved through rigorous, repeated testing. In his laboratory notebooks, he often recalibrated an electrometer a dozen times in a single day, each time refining its accuracy further. With each iteration, Rutherford pushed the electrometer beyond what anyone thought possible. His efforts paid off. The refined device became capable of detecting charges so minute that they were considered undetectable before his improvements. These charges were produced when radiation ionized the air inside an experimental chamber, meaning the electrometer could now indirectly measure the intensity of radioactive emission with extraordinary sensitivity. This capability transformed the study of radioactivity. Researchers were no longer limited to vague observations. They could now quantify ionization levels, compare materials, and understand radiation behavior in mathematical detail. Rutherford soon discovered that using the electrometer to measure ionization currents opened the door to a whole new form of scientific knowledge. When a radioactive substance emitted particles, These particles collided with air molecules, freeing electrons and creating ions. These ions carried tiny electric charges, and the electrometer was now sensitive enough to detect them. This meant that Rutherford could use the electrometer to count the effects of radioactive emission. Each ionization event contributed to the total electric charge measured, allowing him to calculate how active a sample was. This was the first step toward turning radioactivity into a measurable phenomenon. One of the most impressive achievements that came from Rutherford's refined electrometer was his ability to distinguish between different types of radioactive emissions. Before him, alpha and beta rays were simply known as rays, without clear understanding of their nature. But Rutherford, using his precise electrometer, observed distinct patterns in how these emissions ionized air. Alpha particles created dense, strong ionization over short distances, while beta particles produced weaker, more diffuse ionization over longer distances. These subtle differences had been invisible to earlier scientists, but Rutherford's electrometer captured them with clarity. This insight was one of the major breakthroughs that led him to classify alpha and beta radiation as fundamentally different particles. The electrometer also played a crucial role in Rutherford's research on the longevity and decay of radioactive substances. Using the device, he measured how the ionization produced by a sample changed over time. Day by day, week by week, he watched the readings fall slowly and consistently. These observations gave birth to the concept of the radioactive half-life, one of the most important discoveries in nuclear physics. Without an instrument capable of detecting tiny changes in radioactive intensity, the gradual decrease would have gone unnoticed or untrustworthy. The electrometer was the silent partner behind this breakthrough, faithfully recording invisible shifts in atomic activity. Rutherford's refinements also allowed him to measure the speed and range of alpha particles. By placing his electrometer at various distances from a radioactive source, he recorded how the ionization strength decreased with distance. When paired with thin layers of metal or other materials, he learned how far alpha particles could penetrate before being stopped. This work helped establish the now well-known fact that alpha particles have high ionization power but low penetration. Again, none of this would have been possible without the electrometer's extraordinary sensitivity. His electrometer became so reliable that other scientists began requesting copies of Rutherford's design. He shared his methods freely, believing that science advanced faster when tools were standardized. Soon, laboratories across Europe were using electrometers modeled after Rutherford's refinements. As more scientists adopted these instruments, radioactivity research accelerated dramatically. Suddenly, findings made in one laboratory could be verified in another, because the tools were now accurate enough to produce consistent results. This global harmony in measurement, something modern science takes for granted, was possible because Rutherford proved that precise instrumentation was achievable. What made Rutherford exceptional was not merely that he refined an instrument, but that he did so while pushing the boundaries of scientific knowledge. He wasn't improving the electrometer in a vacuum, he was solving scientific problems and creating new ones to test his inventions. Every refinement served a purpose, and every purpose advanced atomic science. His electrometer became a kind of bridge between observable physical effects and the deep, hidden processes occurring inside atoms. Rutherford's electrometer became so central to his work that he once remarked he felt he could hear radiation through its responses. To him, the instrument was not simply a tool. It was an extension of his scientific senses. It translated the invisible into the measurable, the silent into the countable, the mysterious into the knowable. It allowed Rutherford to study the atom not through speculation, but through reliable, precise, consistent data. This shift from intuitive science to precision science marked a turning point in the history of physics. The electrometer's impact extended far beyond Rutherford's own experiments. It influenced entire generations of scientists. Many of Rutherford's students, such as Niels Bohr, Hans Geiger, and James Chadwick, would later become giants in nuclear physics themselves. Each of them learned the discipline of precise measurement from Rutherford, and each carried that discipline into their own groundbreaking research. From early radiation detectors to the Geiger counter itself, echoes of Rutherford's electrometer can be found throughout the evolution of scientific instrumentation. How Rutherford's tools became a global blueprint for investigating the invisible. Rutherford didn't just build instruments, he built templates for how future scientists would think. How his designs, habits, and experimental style spread through labs worldwide, shaping the future of nuclear physics, atomic structure, chemistry, medicine, and even national scientific culture. His tools weren't local gadgets. They became the language of atomic exploration. The new scientific culture Rutherford created when Rutherford introduced his electrifying chamber setups, alpha detectors, and ionization techniques. Something subtle but radical happened. Science started to expect more precision. Before him, researchers were often satisfied with broad observations. This material glows. This mineral is radioactive. This ray seems to behave like that. It was descriptive, loose, observational. Rutherford forced the entire world to level up. His tools demanded numbers, not vibes. Exact values, not guesses. Rates, intensities, angles, distances. You couldn't use one of his techniques without treating nature like a puzzle with measurable pieces. And once his methods spread, every serious lab on Earth had to match that standard or risk looking outdated. It's kind of like how smartphones forced old flip phones into retirement. After a breakthrough, everything else just feels ancient. Rutherford's tools weren't just used. They were imitated, scaled, remixed, refined, cloned until Rutherford-style experimentation was basically its own scientific dialect. Influencing the next wave, Bohr, Geiger, Marston, and a whole lineage. Let's make this personal for a sec. Rutherford wasn't the type of boss scientist who sat in a big leather chair giving vague advice. He was hands-on, running around the lab, cracking jokes, yelling numbers, and literally soldering wires mid-experiment. His students absorbed not only his teachings but his style, meticulous, fearless, playful, and extremely stubborn in the face of doubt. Geiger and Marston, they began as assistants helping Rutherford test alpha scattering. Soon they were using his detectors with such confidence that even he trusted their data. They mastered his devices so well that they could troubleshoot them faster than other researchers could even set them up. His tools didn't just shape experiments, they shaped people. Niels Bohr learned from Rutherford's measurements that atoms weren't mushy clouds. They were structured systems with compact cores. Rutherford's instruments didn't propose a theory, they exposed a fact. Bohr built the quantum model on top of Rutherford's data because the measurements were so precise they demanded explanation. The ripple lineage, every generation afterward, scattering physicists, nuclear chemists, radiologists, particle physicists, essentially learned to measure like Rutherford. Start with a controlled source, set up a sensitive detector, measure changes in charge, position, or energy, repeat until nature gives up her secrets, that workflow. That's Rutherford, that's his legacy. His tools weren't gadgets. They were mentorship embodied in technology, revolutionizing how scientists saw the invisible world. Before Rutherford's era, scientists relied heavily on their eyes. Magnifying glasses, telescopes, flame colors, crystallography, they built their work around visible phenomena. Rutherford flipped the script. You don't need to see something with your eyes. You can detect its effects. It's a philosophical shift, a confidence shift, and honestly, a vibe shift in science. His tools taught researchers that invisible particles leave visible marks. Subatomic events create detectable ionization. Tiny emissions can be counted, tracked, cataloged. The unseen world is not unreachable, you just need better instruments. This changed everything. Suddenly, the atom wasn't a theoretical object in a textbook. It became a place you could probe, disturb, interrogate, measure. Even today, every particle detector at CERN, the massive billion-dollar colliders, is essentially a advanced descendant of Rutherford's tools. His legacy is alive in every click of every detector ever made. Creating the framework for nuclear medicine, this is the part most people underestimate. Rutherford never set out to cure diseases. He wasn't writing medical papers or building hospital equipment. But his tools helped create the logic behind nuclear medicine. If you can measure radioactive emissions, and you can track them through materials, then you can track them through human tissue. Boom, that's the foundation of PET scans, radiation therapy, radioisotope diagnostics, tracer techniques, targeted cancer treatments, every medical isotope used today, iodine-131, technetium-99m. Radium treatments relies on measurement techniques Rutherford helped pioneer. Ionization chambers, counting devices, precise activity measurements. He gave medicine the tools to see inside the body without cutting it open. His influence slipped from physics labs into clinics, hospitals, imaging centers, transforming human health without him ever stepping into the medical field. That's the wild thing. A man studying atomic particles ended up reshaping how we diagnose and treat diseases. Building global standards for radiation safety, another domino effect of Rutherford's tools. They made radiation measurable. And once something is measurable, it becomes manageable. Governments, industries, and labs around the world began writing safety standards based on the kinds of measurements his devices made possible. Safe exposure limits, shielding requirements, contamination detection, dose monitoring, industrial radiography, regulations. Imagine trying to regulate radiation without reliable counters or detectors. It would have been chaos. Rutherford didn't just create tools, he created predictability. His methods allowed radiation to become quantifiable, not mysterious. This unlocked entire industries: nuclear power, radiographic materials analysis, radioactive dating, and more. If radiation safety is like traffic laws, Rutherford invented the first speedometer. Transforming chemistry into a quantitative nuclear science, chemists used to think of elements as eternal and unchanging. Radioactivity blew that concept apart, but it was Rutherford's tools that let chemists actually measure those transformations. Decay chains, half-lives, elemental transmutations, isotopic behavior. Suddenly, chemistry wasn't just about reactions, it was about transformations inside the nucleus. The periodic table became a living, dynamic system where elements decayed, evolved, and morphed. Rutherford's detectors and counting methods made nuclear chemistry possible, giving scientists the confidence to classify isotopes, map decay sequences, and measure tiny emissions that no human eye could ever see. The chemistry of the nucleus was born from Rutherford's instrumentation. The global spread of the Rutherford laboratory culture. Rutherford didn't patent his tools or guard them like secrets. He wanted the world to use them, so he published everything: designs, diagrams, measurements, methods. As a result, German labs copied his counters, French labs improved his chambers, American labs scaled his techniques. Soviet labs rebuilt his alpha detectors. British labs refined his radon measurement systems. His lab at Manchester became something like the Mecca of nuclear physics. People traveled internationally just to see how he arranged apparatus on benches, how he calibrated instruments, how he trained students. This was the beginning of globalized physics collaboration, long before the internet, before email, before Zoom. Rutherford's tools spread the same way music genres do, through excitement, imitation, and transformation. His influence wasn't centralized, it was viral. The evolution of his tools into modern particle physics equipment. Let's break this down in a fun way. Imagine Rutherford's tools as the baby versions of today's machines. His alpha detectors, right arrow modern scintillation detectors, his ionization chambers, right arrow Geiger counters, right arrow multi-wire chambers, his scattering experiments, right arrow particle accelerators, his radon measurement systems, right arrow isotope labs, his radiation counters, right arrow PT scanners, CT detectors, X-ray sensors, everything scaled upward. Bigger energy, faster particles, stronger magnets, more sensitive electronics. But the logic behind the machines stayed rooted in Rutherford's original approach: produce particles, send them into matter, measure the aftermath, extract the structure. It's the original recipe, just cooked with fancier ingredients. Rutherford was essentially the first DJ of particle physics. He laid down the beat, and everyone else remixed it. Why his tools created a new era of scientific confidence. Before Rutherford, atomic theories were, let's be honest, kinda shaky. People argued, guessed, speculated. Some models were almost philosophical. Rutherford's tools changed that. Now you could measure particle paths, predict scattering angles, track radioactive decay, detect emission signatures. His tools injected hard evidence into a field that desperately needed clarity. Suddenly, theories had to match data, not the other way around. And when scientists saw that the invisible world could be measured with such accuracy, they got bold. They pushed harder. They asked crazier questions. Rutherford's tools didn't just enable discoveries. They emboldened scientists to attempt them. He didn't give them answers, he gave them courage. Conclusion: the tools that changed the world. The second keynote's Part B is really about appreciating that Rutherford's tools of discovery were far more than wooden boxes, wires, foil sheets, and glass chambers. They were a new scientific mindset, a new global culture of precision, a new generation of scientists, a new method for studying the invisible, the foundation of nuclear medicine, the birth of modern particle detectors, the backbone of radiation safety, the spark that ignited atomic theory's biggest revolutions. Rutherford wasn't trying to change the whole world. He was just trying to measure a few mysterious rays. But when you look at the global impact, the medical revolution, the scientific culture he created, and the generations of researchers who depended on his approach, it's clear that his tools didn't just detect particles. They detected the beginning of a new scientific era. Ernest Rutherford's gold foil experiment stands as one of the most iconic milestones in the history of modern physics. Conducted in 1909, it was not merely an experiment. It was a revelation that fundamentally reshaped humanity's understanding of matter. To fully appreciate its significance, one must consider the scientific context of the time. At the beginning of the 20th century, the structure of the atom was largely speculative. The dominant model proposed by J. Thomson described the atom as a plum pudding, a diffuse cloud of positive charge with negatively charged electrons embedded randomly, much like plums within a pudding. While this model accounted for the atom's overall neutrality, it lacked predictive power for behaviors observed in radioactive decay and scattering experiments. Rutherford, along with his collaborators Hans Geiger and Ernest Marston, set out to test this prevailing model. They designed an experiment in which alpha particles, positively charged particles emitted from radioactive sources, were directed at an ultra-thin sheet of gold foil. Surrounding the foil, they placed a fluorescent screen coated with zinc sulfide, which would emit tiny flashes of light whenever struck by an alpha particle. By carefully observing these flashes, the team could infer the trajectories of the alpha particles after they encountered the gold atoms. What they found was startling. Most of the alpha particles passed through the gold foil with little or no deflection, suggesting that the majority of an atom is empty space. However, a small fraction of particles were deflected at large angles, with some bouncing almost directly back toward the source. Such dramatic deflections were entirely inconsistent with the plum pudding model, which predicted only minor scattering. Rutherford himself famously remarked that it was as if you fired a 50-inch shell at a piece of tissue paper, and it came back and hit you. This vivid analogy illustrates the shocking nature of the results. The atom's positive charge and mass must be concentrated in a tiny, dense nucleus capable of repelling the incoming alpha particles. The implications of the gold foil experiment were profound. Rutherford proposed a new atomic model, a dense, positively charged nucleus at the center, surrounded by electrons moving through the vast empty space around it. This nuclear model of the atom not only explained the unexpected scattering of alpha particles, but also paved the way for the development of quantum mechanics and the study of subatomic particles. By establishing that atoms have a concentrated nucleus, Rutherford provided the framework for understanding chemical behavior, nuclear reactions, and radioactive decay processes. His insight into the atom's structure would later influence Niels Bohr's planetary model, which incorporated quantized electron orbits and ultimately led to the sophisticated quantum models we use today. The gold foil experiment also exemplifies the power of experimental ingenuity. Rutherford's team had to overcome numerous technical challenges to make this discovery possible. They had to produce an extremely thin sheet of gold, only a few atoms thick, to allow alpha particles to pass through while still interacting with the atomic nuclei. They developed sensitive detection methods to observe the fleeting flashes on the zinc sulfide screen, a process requiring meticulous attention and repeated verification. Each observed deflection represented not only a data point, but a tiny clue in deciphering the atomic mystery. The experiment's elegance lay in its simplicity. A straightforward setup yielded insights of staggering complexity. Moreover, the gold foil experiment marked a critical moment in the study of radioactivity. Prior to Rutherford, radioactivity was largely a phenomenological curiosity, observed but poorly understood. By connecting the behavior of alpha particles to the internal structure of the atom, Rutherford linked radioactivity to the nucleus itself. This conceptual leap transformed radioactivity from an enigmatic phenomenon into a scientifically tractable field. Researchers could now explore the forces within the nucleus, investigate nuclear transmutations, and ultimately harness nuclear energy. The experiment also underscored the interplay between theory and observation. Rutherford's willingness to challenge prevailing ideas and interpret surprising results exemplified the scientific method at its most rigorous. Finally, the legacy of the gold foil experiment extends beyond physics. It represents a paradigm shift in human thought, challenging assumptions about the invisible building blocks of matter. It inspired generations of scientists to question established models, to seek evidence in unexpected places, and to embrace the uncertainty inherent in discovery. Rutherford's meticulous experimentation, combined with bold theoretical insight, demonstrates that groundbreaking science often arises at the intersection of careful observation and imaginative interpretation. The gold foil experiment remains a powerful symbol of intellectual courage and precision, a moment when humanity glimpsed the hidden architecture of the natural world for the first time. Following the groundbreaking gold foil experiment, Ernest Rutherford's attention turned to probing the contents of the nucleus itself. While the nuclear model revealed that atoms have a dense, positively charged center, the composition of this nucleus remained a mystery. What particles constituted it? How did they interact? These questions drove Rutherford to embark on a series of experiments that would eventually lead to the discovery of the proton, one of the fundamental building blocks of matter. This fourth keynote highlights the meticulous experimental work, theoretical insight, and visionary thinking that enabled Rutherford to reveal the proton and further revolutionize atomic science. By 1917, Rutherford was experimenting with the bombardment of light elements using alpha particles. He hypothesized that when alpha particles collide with certain nuclei, nuclear reactions might occur, producing new particles or transmuting elements. This was a daring idea, as transmutation of elements had previously been considered alchemy, a mystical practice rather than a scientific one. Yet, Rutherford approached it with precision and discipline, employing the same methodological rigor that had defined his earlier experiments. His laboratory became a stage where the unseen world of nuclear particles was coaxed into revealing its secrets. In one pivotal experiment, Rutherford directed alpha particles at nitrogen gas. By observing the results using a scintillation screen, he noticed peculiar traces indicating that positively charged particles were being emitted from the nitrogen nuclei. Detailed analysis revealed that these emissions were hydrogen nuclei, which Rutherford interpreted as a fundamental constituent of atomic nuclei. In other words, he had discovered that hydrogen nuclei, later named protons, were present within the nuclei of heavier elements. This insight was monumental. It established that protons were not just parts of hydrogen atoms, but were universal building blocks of all atomic nuclei. The discovery of the proton carried profound theoretical implications. First, it provided a natural explanation for the identity and chemical behavior of elements. If the number of protons in a nucleus determines the element's atomic number, then the periodic table could be understood in terms of nuclear composition rather than just electron arrangements. Rutherford's work bridged the gap between chemistry and physics, linking the observable chemical properties of elements to their underlying nuclear structure. Second, the proton's identification allowed scientists to begin exploring nuclear forces, the interactions that hold protons and neutrons together against the repulsive electromagnetic force between positively charged protons. This opened a new realm of inquiry into nuclear physics, eventually leading to the discovery of the neutron, nuclear binding energy, and the principles underlying both fission and fusion. Rutherford's method exemplified the combination of creativity and rigor essential to scientific discovery. He did not rely solely on theoretical speculation, but instead designed experiments that could yield measurable, interpretable results. Using alpha particle bombardment, He observed the behavior of nuclei under extreme conditions, translating fleeting scintillations on a screen into a profound understanding of atomic structure. Each flash represented not a mere point of light, but a window into the hidden architecture of matter. This approach exemplified Rutherford's philosophy. The most abstract questions about the universe must be addressed with precise and reproducible experimental evidence. Furthermore, the discovery of the proton underscores the importance of perseverance in scientific inquiry. Early experiments were often ambiguous or difficult to interpret, as detection methods were primitive by modern standards. Rutherford and his collaborators had to distinguish genuine signals from background noise, account for experimental errors, and repeat procedures countless times to ensure validity. This painstaking work demanded patience, keen observation, and the ability to interpret subtle patterns in data, a hallmark of Rutherford's genius. His success illustrates that major breakthroughs often emerge not from sudden inspiration alone, but from sustained, careful experimentation. The proton also had wider implications beyond the laboratory. It transformed humanity's conception of matter from an abstract, indivisible particle into a complex, structured system governed by internal components. Understanding that protons, along with electrons and later neutrons, form the nucleus provided a conceptual framework for nuclear chemistry, astrophysics, and particle physics. It enabled scientists to begin asking deeper questions. How many protons exist in a particular nucleus? What determines nuclear stability? How do nuclear reactions power stars or produce radioactive decay? These inquiries, sparked by Rutherford's discovery, continue to drive scientific exploration to this day. Finally, the discovery of the proton reflects Rutherford's broader legacy as a pioneer of experimental physics. He demonstrated that by carefully probing the invisible, one could reveal fundamental truths about the natural world. His work transformed abstract hypotheses into observable, measurable reality, bridging the gap between theory and experiment. By uncovering the proton, Rutherford laid the foundation for modern nuclear physics, influencing generations of scientists, from Niels Bohr to James Chadwick and beyond. His ability to see beyond existing models, combined with his commitment to empirical evidence, exemplifies the essence of scientific innovation. One of Ernest Rutherford's most transformative contributions to science was his pioneering work in nuclear transmutation, the conversion of one element into another through radioactive decay. This fifth keynote highlights how Rutherford's experiments went beyond mere observation of radioactivity, demonstrating that the atom is not an immutable entity, but a dynamic system subject to internal transformations. His work in this area not only established the principles of nuclear chemistry, but also laid the groundwork for modern nuclear physics and the eventual harnessing of nuclear energy. At the dawn of the 20th century, radioactivity was largely a mysterious phenomenon. Scientists knew that elements like uranium and radium emitted radiation spontaneously, but the mechanism behind this emission was unclear. Rutherford's brilliance lay in his ability to combine keen observation with innovative experimentation to uncover the processes driving these transformations. By carefully studying the decay of radioactive elements, he recognized patterns that suggested the existence of intermediate products and that atomic nuclei could transmute over time into different elements. Rutherford's experiments with alpha particles and radioactive substances led to the first artificial nuclear reaction. In 1919, while bombarding nitrogen gas with alpha particles, he observed the emission of hydrogen nuclei. Through meticulous analysis, Rutherford concluded that the nitrogen nuclei had been transformed into oxygen, a direct observation of one element changing into another. This landmark achievement marked the birth of artificial nuclear transmutation, demonstrating experimentally what had been theorized only in speculative terms. Atoms could indeed be altered at the nuclear level. The significance of Rutherford's work in transmutation extends beyond the laboratory. Philosophically, it shattered the ancient notion of the atom as indivisible and immutable. For centuries, the atom had been considered the fundamental, unchangeable unit of matter, a concept dating back to the ideas of Democritus. Rutherford's discovery showed that the nucleus, far from being static, could undergo profound transformations. This revelation fundamentally altered the scientific understanding of matter and inspired generations of physicists and chemists to explore nuclear reactions, radioactive decay chains, and, ultimately, the forces that govern atomic stability. Rutherford's work in nuclear transmutation also established critical experimental techniques that would define the field of nuclear physics. The careful preparation of radioactive sources, precise detection of emitted particles, and interpretation of scattering patterns were all methods refined in Rutherford's laboratory. By quantifying the energy and trajectories of emitted alpha and beta particles, he could infer the structural and energetic changes occurring within nuclei. These techniques became foundational tools, employed by future scientists such as James Chadwick, who discovered the neutron, and Enrico Fermi, who conducted pioneering work on nuclear fission. The discovery of transmutation also had practical and scientific consequences. By demonstrating that atomic nuclei could be altered, Rutherford laid the conceptual groundwork for the creation of isotopes atoms of the same element with different numbers of neutrons, and for understanding radioactive decay chains that produce stable elements from unstable ones. This knowledge became crucial for fields ranging from radiochemistry and nuclear medicine to astrophysics, where nuclear reactions in stars drive the formation of elements in the universe. Without Rutherford's meticulous identification of nuclear transformation, these areas of research might have developed far more slowly. Furthermore, Rutherford's work exemplifies the power of blending theory with experimentation. He approached radioactive decay with a model-driven mindset, seeking not just to catalog observed phenomena, but to interpret them within a coherent theoretical framework. He realized that the energy emitted during radioactive decay was enormous compared to chemical reactions, implying that the source of this energy lay deep within the nucleus. This insight foreshadowed later discoveries of nuclear binding energy and the enormous potential contained within atomic nuclei knowledge that underpins both nuclear power and our understanding of stellar processes. The social and scientific impact of Rutherford's transmutation work cannot be overstated. It helped elevate the study of radioactivity from a curiosity into a rigorous scientific discipline. His discoveries inspired contemporaries and students alike, including Niels Bohr and Frederick Soddy, to pursue research in atomic and nuclear phenomena. Rutherford's approach, combining careful observation, quantitative measurement, and bold theoretical interpretation, became a model for future scientific inquiry. Moreover, his work instilled confidence that humanity could probe and even manipulate the most fundamental constituents of nature. Finally, Rutherford's pioneering of nuclear transmutation demonstrates the profound interplay between imagination and evidence in scientific discovery. He envisioned the atom as a dynamic, malleable structure long before others accepted this possibility. Yet he did not rely solely on speculation. He constructed precise experiments to test his ideas. The successful demonstration that nitrogen could be converted into oxygen was not merely a technical achievement, but a conceptual breakthrough, showing the malleability of matter itself. This blend of visionary thinking and empirical rigor remains a hallmark of Rutherford's scientific legacy. After uncovering the nuclear model of the atom and identifying its constituent proton, Ernest Rutherford's curiosity naturally extended to understanding the forces that hold the nucleus together. While the existence of a dense, positively charged nucleus explained many experimental results, it raised a profound question: how could so many positively charged protons coexist in such close proximity without repelling each other violently? This keynote explores Rutherford's efforts to probe these fundamental nuclear forces, laying the groundwork for modern nuclear physics and providing insight into the powerful interactions governing matter at its most fundamental level. The puzzle of nuclear stability emerged immediately after Rutherford proposed the nuclear model. According to classical physics, the electrostatic repulsion between protons should cause the nucleus to fly apart, as like charges repel. Yet, experiments showed that most atomic nuclei were remarkably stable. Rutherford recognized that there must be an additional, attractive force within the nucleus, one capable of counteracting the repulsive electromagnetic force. Although he could not fully define this force, his investigations marked the beginning of a new era in understanding the strong interactions at the heart of atoms. Rutherford's approach combined ingenious experimentation with careful theoretical reasoning. Using alpha particle scattering and radioactive decay observations, he examined the energy, direction, and frequency of emitted particles. Each observation provided clues about the interactions taking place within the nucleus. For instance, the energy released in alpha decay suggested that a tremendous amount of energy was stored within the nucleus, far exceeding the energy involved in chemical reactions. Rutherford inferred that this energy must be tied to the strong binding forces holding nuclear components together. This insight was pivotal, as it suggested that the nucleus was not just a simple cluster of protons, but a dynamic system governed by internal forces. One of Rutherford's key strategies was to study nuclear reactions induced by particle bombardment. By observing how nuclei responded when struck by alpha particles, he could infer properties of nuclear forces. For example, the deflection, absorption, or transmutation of target nuclei provided indirect evidence of the forces acting over extremely short ranges. Rutherford realized that the forces binding the nucleus must be powerful yet extremely localized, operating only within distances comparable to nuclear dimensions. This conceptual leap laid the foundation for later theories of the strong nuclear force, eventually formalized through quantum mechanics and particle physics. Rutherford's investigations into nuclear forces also contributed to understanding nuclear decay processes. He observed that certain nuclei spontaneously emitted alpha or beta particles, transforming into other elements in the process. These decay processes implied that the nucleus was not merely a static structure, but a system capable of reconfiguring itself when energy thresholds were surpassed. By connecting the behavior of radioactive nuclei with the underlying forces, Rutherford provided a framework for predicting nuclear stability and decay patterns. His work anticipated the later development of models explaining isotopic stability and the lifetimes of radioactive elements. Furthermore, Rutherford's pursuit of nuclear forces illustrates his characteristic blend of imagination and empirical rigor. He proposed bold theoretical ideas while grounding them in careful experimentation. Although he did not identify the strong nuclear force in modern terms a discovery that would come decades later, he correctly hypothesized that an extremely strong attractive interaction must exist within the nucleus to counteract electrostatic repulsion. This insight was crucial for the later work of scientists such as James Chadwick, Heidke Yukawa, and Enrico Fermi, who built upon Rutherford's pioneering observations to formalize the forces and interactions governing subatomic particles. The exploration of nuclear forces also had far-reaching implications for energy science. By demonstrating that immense energy was stored within the nucleus, Rutherford opened the conceptual pathway to harnessing this energy in controlled ways. Understanding nuclear forces became essential for the eventual development of nuclear power and the study of fission and fusion reactions. Rutherford himself was careful to emphasize the theoretical possibilities without immediate practical applications, but his work laid the intellectual groundwork for future breakthroughs in energy generation and nuclear technology. Rutherford's study of nuclear forces further reflects the philosophy underpinning his scientific approach. He combined meticulous measurement with conceptual boldness, showing that even phenomena invisible to the naked eye could be analyzed and understood through careful inference. Each experimental observation, whether it was the scattering angle of an alpha particle or the energy of an emitted particle, became evidence to probe deeper into the hidden architecture of the nucleus. By interpreting these results, Rutherford expanded the frontiers of human knowledge, revealing a universe far more complex and dynamic than previously imagined. Finally, the exploration of nuclear forces illustrates the broader significance of Rutherford's contributions. It marked the transition from describing atoms as static entities to understanding them as dynamic systems with internal interactions. This shift in perspective was crucial for the development of nuclear physics, particle physics, and quantum theory. Rutherford's insights enabled subsequent generations to map the structure of the nucleus, discover new particles, and investigate the fundamental forces governing matter. His work reminds us that scientific discovery is often a process of uncovering hidden mechanisms and connecting observations to underlying principles, rather than merely cataloging visible phenomena. Ernest Rutherford's contributions to the understanding of radioactivity and atomic structure did not end with individual discoveries. They created a foundation that would influence the entire course of modern science. The seventh keynote emphasizes the lasting legacy of his work, demonstrating how his insights into the atom and nucleus shaped the development of nuclear physics, chemistry, and even cosmology. Rutherford's legacy is not just in the experiments he conducted, but in the methodological and conceptual framework he provided, which continues to guide scientific inquiry to this day. Rutherford's work transformed the way humanity perceives matter. By demonstrating that atoms have a dense nucleus and identifying the proton as a fundamental constituent, he challenged centuries of assumptions that the atom was indivisible and immutable. This shift in perspective opened the door to the study of subatomic particles, nuclear reactions, and quantum mechanics. The recognition that matter is dynamic and structured at a microscopic level allowed scientists to approach problems in physics and chemistry with unprecedented sophistication. Rutherford's insights provided the scaffold upon which the theories of Niels Bohr, James Chadwick, and other pioneers were built. One of the most profound aspects of Rutherford's legacy is his establishment of experimental rigor as a cornerstone of scientific research. His approach emphasized careful measurement, innovative use of technology, and precise interpretation of data. Whether it was the meticulous tracking of alpha particles in the gold foil experiment or the detection of protons in nuclear reactions, Rutherford demonstrated that profound scientific truths could be inferred from careful observation and quantitative analysis. This methodological standard became a model for subsequent generations of physicists, guiding experimental design and encouraging a culture of meticulous scientific investigation. Rutherford also contributed to the conceptual unification of chemistry and physics. By showing that chemical elements could transform through nuclear reactions, he bridged a gap between the microscopic forces governing atomic nuclei and the macroscopic properties observed in chemical behavior. His work helped establish nuclear chemistry as a distinct field, which investigates isotopes, radioactive decay, and transmutation. This conceptual link between the microscopic and macroscopic worlds remains a fundamental principle in science, influencing research in materials science, energy generation, and even medicine through applications such as nuclear imaging and radiotherapy. The practical implications of Rutherford's discoveries further amplify his enduring impact. His identification of nuclear structure and the energy contained within the atom provided the intellectual foundation for harnessing nuclear reactions, both in power generation and in scientific research. While Rutherford himself focused on basic science rather than applied technology, his work indirectly enabled the development of nuclear energy and advanced the study of atomic nuclei in both theoretical and applied contexts. This influence underscores the importance of foundational research in enabling transformative technological advancements. Rutherford's mentorship and leadership also form a key part of his legacy. Throughout his career, he trained and inspired a generation of scientists who went on to make their own groundbreaking contributions. Notable students and collaborators, including Niels Bohr, Hans Geiger, and James Chadwick, benefited from Rutherford's guidance and approach to experimentation. By fostering a culture of curiosity, precision, and intellectual daring, he multiplied the impact of his discoveries far beyond his own direct work. In this way, Rutherford's influence extends not only through his experiments, but through the intellectual lineage of scientists he shaped. Beyond the laboratory, Rutherford's contributions have had a lasting impact on scientific thought and philosophy. His work exemplifies the power of observation, experimentation, and inference in uncovering the hidden structures of nature. The concept of the atom as a structured, dynamic system fundamentally altered humanity's understanding of matter and energy, laying the groundwork for later advances in quantum theory, particle physics, and cosmology. Rutherford's discoveries exemplify the principle that careful investigation of the smallest scales can yield insights with universal significance, shaping not just science, but the broader intellectual world view. Rutherford's legacy is also evident in the language and framework of modern physics. Terms such as nucleus, proton, and radioactive decay have become standard, reflecting the enduring influence of his discoveries. His models of atomic structure, though refined by later quantum theory, remain the conceptual starting point for understanding nuclear and particle physics. By defining fundamental concepts and experimental approaches, Rutherford provided tools that scientists continue to use in exploring the most fundamental questions of nature, from the behavior of subatomic particles to the processes powering stars. Finally, the broader cultural and scientific impact of Rutherford's work highlights the timeless relevance of fundamental research. His discoveries transformed human understanding of the universe, revealing that matter is not static but dynamic, structured, and capable of transformation. By illuminating the nucleus and its components, Rutherford provided a lens through which scientists could explore both the microscopic and cosmic realms. His work continues to inspire curiosity, innovation, and rigorous inquiry, demonstrating the enduring value of combining experimental skill, theoretical insight, and visionary thinking in pursuit of knowledge.